Here in the Department of Soil Science, we have a wide range of research that's going on, ranging from practical to very basic research. My own research in soil chemistry lies on the basic end of the spectrum. So we try to understand how plant nutrients and potentially toxic contaminants in the environment bind in soils so that we can maximize, in terms of nutrients, the uptake by crops and minimize the detrimental environmental impacts of contaminants. We approach the problem by doing molecular spectroscopy to understand the fundamental mechanisms by which chemical elements bind in soils. For example, we had been involved years ago with some soil remediation issues at the Marine Corps Air Station in Cherry Point, North Carolina, where they had contaminations of lead and chromium and zinc and copper and other heavy metals in some land areas. And we helped identify the best way to manage that land using our spectroscopic techniques. Currently, we have a grant from the Tennessee Valley Authority to help determine the long-term impacts of a major coal fly ash spill. And we're looking at the chemistry of the fly ash and its potential impacts on some river systems in which 1 billion gallons or more of fly ash was basically released into 2 major river systems in Tennessee. There's concern about the heavy metals that are in fly ash, lead, arsenic, selenium, and other potentially toxic elements, and their impact on the ecosystems and on human health. We also have a very basic research project in which we're developing means to essentially perform soil chemistry on a micro scale, or ideally on a nanoscale in soils. So for example, we can try to understand exactly how these chemicals bind by looking at very, very small spatial scales. In the ideal world, we could look almost at the molecular level, but the technology has not been developed yet. We do use very advanced technologies in our research. We do a lot of our work at national laboratories that are supported by the Department of Energy, particularly the National Synchrotron Light Source up in Brookhaven National Laboratory, which is on Long Island in New York, and also another facility up at the Advanced Photon Source near Chicago, Illinois. Specifically, what we use are synchrotron X-ray facilities. A synchrotron is basically a large electron accelerator ring that produces extremely intense X-rays, and these extremely intense X-rays allow us to look at chemical binding mechanisms in soils. But what's exciting right now is we're trying to do chemistry on a micro scale. So for example, we use an X-ray beam that can be focused down to, in some cases, 10 microns. And in other cases, when we look at phosphorus, we've made maps of soil particles with a spatial resolution of 40 nanometers, which is very small. This approach essentially segregates the different chemical constituents in the soil so we can look at them much more closely, and then we can do what's called molecular spectroscopy to try to understand how the element is bound in the soil. I believe research has a bright future, and I believe that because of the nature of the very complex and large problems that we're dealing with in society, that very good connections and collaborations between the private sector, universities, and the government working towards solving particular problems will be the most fruitful way to go forward.